Our speaker today is Stefano Decio, who's one of our first year, and we talk about the Robin. Actually, you sent me something like the Robin harmonic measure of domains.
Oh, okay. Yes.
Okay.
It's about the same.
So you keep changing it to see if you pay attention.
Great. Thanks a lot, Camilo, for the introduction. Thanks for the opportunity to speak here. Thanks everyone for coming. Okay. So I'm going to tell you about a little bit about the Robin problem in rough domains, or as Camilo was saying, the Robin harmonic measure. So this is everything I'm going to say is based on joint work with Guy David, Max Engelstein, Svitlana, Mayboroda, and Michetti. Okay, and yeah, the paper is not out yet. Hopefully, it will be sometime soon. But yeah, so it's we got a few results, and I'm going to give you an overview of what the work we've done on this. Feel free to stop me at any point. I don't assume people are necessarily familiar with harmonic measure. I mean, some of you are probably more than I am, but yeah. So feel free to stop me at any point. I have no ambition to actually go through everything I want to say, so I'll be okay. Okay, cool. Let's see. So first, let me start with the definition. So what problem I'm talking about? I'm talking about the Robin problem, and I'm going to set it in omega in Rn. It's a bounded domain. Okay, and this will be the thing that could be rough sometimes in the title. I'm going to take an elliptic, a uniformly elliptic bounded matrix A, symmetric. Okay, and positive real number A, little a. So the problem is as follows. I'm trying to solve give a grad u equals 0 in the domain omega with this boundary condition 1 over a, the conormal derivative a grad u dot nu plus u equals to f, where f is some function on the boundary.
No question.
And nu is the outward normal derivative.
Small a and big A, they do depend on the point.
No, sorry, a is a number.
And big A
is not a constant matrix.
is not a.
It's not a constant matrix yet. So a might depend on. Of course, the other normal derivative, I didn't give you anything about the regularity of the domain, so might not make any sense. So what we're actually doing is solving sort of in a weak form. We're trying to find the solution to 1 over a integral over omega a grad u grad phi plus integral over the boundary u phi equals integral over the boundary f phi for phi in some class of test functions. Okay. If you don't like general operators, you can think that we're just solving the Laplace equation, Laplace u equals 0 in the bulk, and then this sort of mixed boundary condition, the normal derivative of u plus u equals f on the boundary. Okay, and a bunch of things I'm gonna say are interesting also in this sort of sort of elementary case in which the matrix A is the identity. Okay. Now this is difficult. I shouldn't use the result. I'm gonna go to the boards with me. Okay, why is this? So this is called maybe we should say this is called the Robin boundary condition. This sort of mix between and you can see that if I take a to infinity, then I get the Dirichlet problem. And if I send a to 0, then I more or less get the Neumann problem. sort of, not really, because I should renormalize the F here. You know, and this makes sense because for the Neumann problem to be well posed, you need, for instance, F to integrate to 0, and this kind of stuff. But morally, I want to think of sort of this Robin problem as interpolating between the Neumann and the Dirichlet problems. So when this parameter A is very small, I want to think of the solution to this problem as being sort of similar to solutions to the Neumann problem. And when this parameter is very large, I want to think of this as similar to the solutions of the Dirichlet problem. And we will see that this sort of makes sense. I hope at least. Okay. Now a little bit of fiction, maybe. Why people are interested in this problem? Turns out that actually, in like for instance, in physics, this Robin boundary condition is like a lot more natural than both the Dirichlet and the Neumann boundary condition. And you can think this is, for instance, used to you can think of omega as the boundary of omega as some kind of like semi-permeable membrane, and this problem describes a steady state process, sort of a kind of like steady state diffusion through a semi-permeable membrane. So some things get through the membrane. So you can think of, for instance, sort of the physics problem from which we started this. Is really sort of used to model the air circulation in the lungs. Okay, the lungs are a semi-permeable membrane, and as physicists do, if you sort of equate fluxes at the boundary, you get this Robin boundary condition on the membrane. Okay, right. Incidentally, we just say sort of this thing about the lungs is interesting because that's where the rough domains come in. You can model the human lungs as a kind of fractal. It's got a tree-like structure, and for instance, I think so. I looked at some biology papers. They estimate the Hausdorff dimension of the lungs as being something like 2.8. So it's pretty close to 3. Right, and this is actually it makes sense from a biological standpoint that the domain is rough because you want to, so the lung is a tree-like structure, and at the end of this tree, there are these things called alveoli, and you want sort of like a large surface area for these alveoli to maximize air circulation, and you want to pack it in sort of such as in a small space. So that's could be, you know, again, this is kind of fiction. I'm not a scientist in this sense, but it could be a motivation for why it's actually interesting to study these problems in domains that are not very small. Okay. Might make some biological sense. Okay. Let's see. Now, maybe let's do some. Let's stop for a second with the fiction, and let's do some maths. And I need to introduce you to the harmonic measure. And to do this, I'm gonna talk to you about the Dirichlet problem for a bit, because that might be a little bit more familiar to some of you, and it was an important motivation for us, and to study this sort of more complicated, maybe, Robin problem. So what is the Dirichlet problem? For simplicity, I'm just gonna do it for the Laplacian now. So everybody knows this, so I'm starting this time in omega Laplace equals 0, and then u equals f on the boundary. So in pretty rough domains, there's some conditions that the domains are co-regular. If you give me a function that is continuous on the boundary, then I can solve the Dirichlet problem with this Dirichlet data. Okay. Not only that, but you can write, there's a representation formula. You can write UF at the point X as an integral over the boundary of the Dirichlet datum F with respect to some measure omega X.
In general,
Yes.
like the only regularity that you have up to the boundary is like continuous.
For the datum F? Yes.
No.
Oh, yeah.
For you, I mean.
Yeah. Okay, so this, so you get a collection of radon measures in this size. These are probability measures in this size by points x in the domain. If I write omega x, then x is called the pole. So omega x is called harmonic measure. With pole at x. Good. So what is, let's try to sort of understand better this, so far it's just a measure, let's try to understand better what it is. So let me take a subset of the boundary, which is for L. And then I define this function u of x, which is the harmonic measure pole of x of this time of the fixed subset. Okay, so this is a function of x, and it turns out that this u is harmonic. It's a harmonic function and solves the Dirichlet problem with the Dirichlet data, the characteristic function, the indicator function of the set E. And it's not a continuous function, but everybody sort of knows. Okay, so you got a nice interpretation once you fix the Borel-Cell set of the boundary and you let the pole vary inside the set omega, you get a harmonic function. So the Dirichlet boundary problem. Okay.
What are you assuming so far about the boundaries?
That it's that the domain is regular, meaning that I can do this thing. It's that to each continuous function I can solve the Dirichlet problem. I don't want to get into the geometry of it, but it's very mild so far. I'm gonna give you something more precise about the boundary when I actually talk about the stuff we did.
Just one question.
Yes.
What does it mean that you solve D with F equal to the characteristic function of E? Like U cannot be continuous, I guess.
Yeah.
So like you want some limit up to the boundary, something like that?
Yes, you can think of it. You can think of it as a weak formulation.
Right. Right.
Okay. There's a nice probabilistic interpretation of this harmonic measure, which if you've ever heard to talk about harmonic measure, you probably have seen this, which is as follows. So again, I'm fixing so this is my domain omega. Here is my E subset of the boundary. I have my point x inside. I start a Brownian motion at the point x. And then it turns out that omega x of E is the probability that the Brownian motion started at the point x. X is the domain omega through the set E. Is this clear enough?
First exit, right?
Sorry? First exits, yes. First exit. Okay, sort of a precise, this is a theorem. It's usually called the Kakutani theorem. Okay. So you got a nice sort of probabilistic interpretation of this harmonic measure being like the hipping measure of a Brownian motion. Okay, so I drew it.
One question. I guess that maybe it's the point. So rough domains, but how rough? Like, can the boundary be very rough?
Well,
Not even rectifiable, not even.
well, for sample, so for the definition to make sense, yes, I'm gonna get into rectifiability in a second.
Oh.
And then you will see that some things go very wrong, but like for the definition in principle, yes, it can be not rectified. Okay. Okay, here I sort of, I drew a fairly nice domain, and then you might think, okay, well, it's clear that, I mean, what could happen, right? You have this Brownian motion, you have a set E on the boundary, well, what's gonna happen? Sort of the harmonic measure, the probability that it has through this set is gonna be comparable to the size of E in the Hausdorff dimension sets, right? Maybe. If you think of nice domains, this makes sense, right? But think of something that is, no, this is gonna be terrible for drawing, but think of a boundary that's sort of like, it's kind of fractal and sort of twists around something. It's got a lot of like twisty things. So then you might think that like, and then the boundary continues like this, that like parts of this boundary are shielded from Brownian travelers, right? If you have something that twists a lot, you might think that, okay, maybe these like Brownian particles will never make it to the end. So the situation is a little more complicated, and there is, I mean, the area, no, I cannot do justice to in just single talks with this area because there's been really a ton of research in this. But sort of, it's an interesting question to ask, like, what do these Brownian travelers? In the sense, you know, more precisely, what is the structure, the support of the harmonic measure? And here, maybe some of the questions of Federico will find an answer. Okay, so the first thing I want to mention, it's a theorem of Makarov, 1985, and then in the formulation that I'm giving, it's due to Johnson-Wolf. A little later. Okay, this is a two-dimensional theorem, so I have the domain is in R2, and they just require its complement to have positive capacity. Then the dimension of harmonic measure is less than 1. And this is sort of, if you will, maybe the first time you see it, it's a surprising theorem, right? The Hausdorff dimension of the boundary of omega could be arbitrarily close to 1. Or arbitrarily close to 2, sorry. Yes, right? So it could be, you can have like a pretty nasty fractal-like object, but sort of the Brownian travelers only see sort of sets of dimension 1 inside this boundary. Yeah, this is for dimension 2. I think as far as I'm aware, Makarov proved it for like simply connected domain, and then this was extended by Johnson.
What do you exactly understand the dimension of the measure?
What is it again? Is it the smallest set of full, the dimension of the smallest set with full measure, right? The smallest dimension of the set with full measure.
Okay, yeah. I mean, not this one.
Yeah.
Exactly. So you are saying what's the dimension of W means?
Dimension of omega?
Yeah.
Yeah, it's dimension in the sense of a measure. What is it? It's
So you take all possible sets
Yeah.
of full measure.
You take
and
all possible-
the
yeah.
list of the dimensions.
yes. So it's not the dimension of the support. In the sense, yeah. I'm not taking the support and saying the dimension as a set. It's a dimension in the sense of measure.
The support is probably huge.
Yes. In this, yeah, because it has to be a closed set. Yeah. Okay.
Or in other words, you're just saying it's absolutely continuous with respect to H1 plus epsilon for any epsilon.
Right.
Something like that, right?
Is that the?
That looks like it will
Yeah.
equivalent to what you're saying.
Yeah.
I mean, you're not saying it's like H1.
Yeah. But yeah. Okay. In higher dimension, the situation is more complicated. Let's see. Let me start actually with sort of a negative result. Wolf, which I believe is from 91. So I have a domain in RD. Sorry, actually, let me say there are examples of domains in RD with the dimension of harmonic measure strictly greater than d-1. Okay. So Makarov's theorem does not hold in higher dimension.
So
Yes.
one question. Like when you write even just the weak formulation.
Yeah.
I guess that you are implicitly assuming that the dimension of the boundary is 1. Otherwise, you'd have to explain to me what's the integral. Like the integral is with respect, the integral on the boundary is with respect to
Is with respect to the Hausdorff measure.
the Hausdorff 1.
Yes. Well, not one. So I'm not talking about the dimension of the wave. Yeah. I mean, you can do. You don't. Okay, you don't need to be codimension one. Most of the talk are going to be codimension one. But okay. So there's Zero Wolf that says that it constructs example of this domain synergy with the dimension of harmonic Dirichlet harmonic measure greater than e minus one. Okay, these are called Wolf snowflakes. On the other hand, there is at least like one positive result due to Bourgain. This is 1987. This is in general the dimension of harmonic measure at least strictly less than the ambient.
Sorry, but wait a second. So
Yes.
if what he said is true, that you need Hn minus one measure of the boundary to be finite to make sense of that.
No, you don't. I don't think you need it.
Okay, but then how do you understand that we to can't integrate over the boundary of omega n times one?
It's, I guess, okay. It's kind of like it's kind of backwards. Like you define the thing so that the integral formulation makes sense.
Like U will be Z, so like if you intersect the boundary with where U is non-zero, most likely you get something that has finite n minus one positive dimension.
Well,
I guess. Otherwise, I don't know how to explain it.
But I mean, okay, we can assume. I mean, all the rest of the talk, especially for the Robin problem, is going to be with finite and positive
okay.
d minus one dimensional.
Okay, but it wouldn't make sense with that theorem if you can't make sense to me.
Which one?
What? I mean, the one of Wolf, right?
Oh yeah.
I mean, to make sense of.
Yeah, but that's a different problem, right? That's the Dirichlet problem.
Ah, okay.
Yeah.
So for the
Here I'm in the Dirichlet setting, right?
The Dirichlet setting.
Yeah. It's I'm trying to give you first the Dirichlet setting, then now all this blackboard is Dirichlet. I'm not talking about that. Okay. This is sort of the standard Brownian motion standard Dirichlet.
Okay, got you.
Okay, cool. All right. Okay, so at least the dimension of harmonic measure is strictly less than the ambient dimension, but after this result of Bourgain, there hasn't really been much more. There are conjectures for what is actually the dimension of harmonic measure. It's a pretty big conjecture, but it's I don't think anyone is really close to proving something. Okay. So now, still in the Dirichlet setting, but now let's assume that the outer dimension of the boundary is finite and positive. Okay? Again, still in the Dirichlet setting. So now I'm going to ask something, a question related to this, but now I want to understand what is the structure of the support of the measure. Okay? So now the dimension will be d minus one. And there's and again, this has been the subject of a lot of work. Let's see. Okay, I apologize. I'm not going to spell out all the names, but I'm gonna tell them. But then I'm just going to write the initials. So this is the field is called the 7 authors paper because it's 7 authors and it's quite a lot. So it's a theorem of Azam, Hoffman, Martel, Mayboroda, Murgoglo, Polsa, Volberg from 2015. Okay, and so the theorem is as follows. So we're in this setting when the Hausdorff measure of the boundary is finite and positive. So you take a Borel subset of the boundary, and I'm sort of, I'm simplifying the result. The result says a lot more, but this is what I want to say. So if you take harmonic measure restricted to this set, and it's mutually absolutely continuous with respect to Hausdorff measure on this set, then E is rectifiable. Okay, this maybe answers part of your questions, Federico. So this is saying is if harmonic measure is well behaved, meaning they see the same zero set with respect to Hausdorff measure, then this set E has to be rectifiable. I'm not going to write out the definition of rectifiability, but what is rectifiable essentially means that it's a countable union of Lipschitz images up to a set of d minus 1 measure 0. Okay, so the set is not too bad. If the harmonic measure is well behaved with respect to surface measure, the set cannot be too bad. Cannot be arbitrarily wild. Okay. Again, the theorem says quite a bit more, but a consequence of the theorem is this.
When you say the symbol that there is between the two measures, it's that one is absolutely continuous with respect to.
That they are mutually absolutely continuous, right? So they see the same zero sets. Okay. That one is correct. Okay. Let's see. There's also a subset of these orders. So this is Azan, Hoffman, Martel, Murgoglu, Polsa. So without Mayboroda and Holberg, this is even more recent. This is maybe the sharpest result. Informally tells you that if you have, let's say, omega quantitatively, absolutely continuous with respect to HD minus 1. This happens if and only if the boundary of omega is uniformly rectifiable plus some topological assumptions. And quantitatively absolutely continuous means some kind of A infinity condition for people that know. Okay, it's well, sort of. I don't want to get too deep into these results. I'm not making them justice. What I want to say is essentially these results are telling you that really rectifiability is the key for Dirichlet harmonic measure. Okay, essentially, good behavior of harmonic measure is equivalent to good behavior in this geometric sense, in the sense of rectifiability. Okay.
One question.
Yes.
Seven authors theorem.
Yes.
It doesn't have a converse.
No, it's not true.
So in general, if
So morally, you want to say that that the harmonic measure is mutually absolutely continuous with respect to surface measure if and only if the boundary is rectifiable. It's not really true.
this is false.
It's yeah, but it's true in this sort of like if you put like quantitatively on both sides, then it's true.
But I think you need some topology. Like
Yes.
if I give a disk
Exactly.
and I remove like a segment, right?
Right.
I mean, going through that segment doesn't mean that you actually leave the
Yeah.
domain. And so the harmonic measure will not see it.
Right.
Yeah.
So some topology is needed.
Some topology is needed, and now I'm going to actually talk a little bit about topology. Okay. So the point of this sort of long discussion about the Dirichlet problem is that this is like the support of harmonic measure, even in the case where it has dimension d minus 1, or even in the case where it has codimension 1, cannot be arbitrary. Let's see. Should I? No, maybe I should go. Maybe I'll go there. Okay. So you can ask. I told you now. Back to Ruben. Let's see. I told you it's still in the blackboard that I sort of think this problem is interpolating between Dirichlet boundary condition, which we just talked at length about, and Neumann boundary condition. So you're like, okay, what is Neumann harmonic measure? Tough luck. The Neumann problem does not have a maximum principle. There's no good way of defining a Neumann harmonic measure. Okay, so that's why I mainly gave you intuition about the Dirichlet case. The Robin problem, whenever. So now I'm going to fix the parameter A of the Robin strictly between 0 and infinity. Whenever A is greater than 0, the Robin problem has maximum principle, and there's a reasonable definition of harmonic measure. Okay. And this is like good part of the talk. So let me now finally put some geometry, more precise geometrical assumptions on the domain omega. Okay, so we want the boundary of omega to be d minus 1 Alfors regular. So this is sort of saying that it's d minus 1 dimensional in a quantitative way, meaning that the measure, the d minus 1 Hausdorff measure of balls of radius are in the boundary scales like r to the d minus 1. Okay. This is the first assumption that we put. This is alpha is regular, d minus 1 alpha is regular. And then we're gonna assume some topology on the domain, namely a couple of things, something called interior corkscrews. So what is this? I have my domain. I have a point on the boundary of the domain. I take a ball of radius r, centered at that point, and then I want to find inside the domain a smaller ball, but of radius comparable to r that is fully contained inside the domain. Okay. What is it's maybe more instructive to say what is a bad thing in this case, or what do we not want, and these are cusps. Okay. A cusp does not satisfy this condition. If you take a ball of radius r at the vertex of the cusp, and you cannot stuff a ball of radius comparable to r inside the cusp, right? Okay. So we want to exclude these things. So we require that we have interior corkscrews, and we also require Harmonic chains.
Just one thing, interior corkscrews, the idea is that for any r, there is a fixed coefficient c, which maybe is very small, and for any r, when you take a ball of radius r, you can find inside a ball of radius cr.
Yes, exactly. Okay. So Harmonic chains, probably have heard about this. Again, I have my domain, and I want that whenever I have 2 points x and y, whose distance from the boundary is not much smaller than the distance between themselves, I can connect them with a chain of balls whose radii, the radii of these balls are comparable to the distance of the balls from the boundary. And I want the chain to have bounded length, sort of uniformly bounded length. Okay. Again, it's maybe more instructive to look at the bad case for this, and Camilla's mentioned this. Yes.
Uniformly bounded length, or you want the length to be comparable to the distance between x?
Yeah, I guess yeah, exactly. It depends on the ratio between the distance of the boundary of x and y and the distance between themselves.
Okay.
Yes. So what is the bad case? Camilla has already mentioned it. You take something like a slit domain, right? Then you have these 2 points x and y that, like, whose distance from the boundary is essentially comparable to the distance between the two. But yeah, but
And you want that to be true only inside, you don't need it to be.
interior, yes. Good point. Interior Harmonic chains. Okay, so these are my 3 conditions. There's sort of absolute regularity of the boundary, interior and interior Harmonic chains. Okay, so the first theorem I'm going to give you, and this is my father's.
And sorry, do you really need a interior corkscrew if you have the interior chain? Because it seems like
I'm not claiming it's sharp, but you need something.
Okay.
Yeah, we don't know what the sharp is. I mean, this is probably complicated.
Okay.
Okay. So the theorem is, let's say omega d minus 1 alphas regulars with interior corkscrews and Harmonic chains. Then we can find a family of radon measures decided by points in omega, such that the solution to the Robin problem in the formulation can be expressed as a u of x as an integral over the boundary with respect to these measures. Okay. So essentially, we're replicating the Dirichlet set. right? We, instead of reconstructing a harmonic function or an aharmonic function from Dirichlet data, we reconstruct it from its Robin data. So from the mixture of the normal derivative and the function at the boundary. Okay, so f is the Robin data. Okay, in the strong formulation, you can think that f at the boundary is the conormal derivative of u plus u. Okay, and then you can
Do you see any regularity on your A, on your matrix?
no, just what I said. So just uniformly elliptic and symmetric. Uniformly elliptic, unbounded, and symmetric. Okay. This theorem, I mean, it's like expected because again, it has a maximum principle. There's like a bunch of elliptic theory hidden into this. Okay, but it's not super surprising. Yes.
It's always a bit the same question. Like, when you state something like this, I expect you to also give me some regularity up to the boundary of U. Otherwise, otherwise you're writing two things, like you inside and you outside. And they have nothing to do one with the other.
So it's right. So for f continuous, you will be continuous up to the boundary.
Fantastic.
That is the simplest. Okay, now I have the problem of where to write. Let's see. I still want the Dirichlet problem for a second because I wanna sort of have the parallel here. Let's see. It's right here. Okay. So now I have this object. I want to try to this Robin harmonic measure, and I want to try to understand it a little bit better. And if you take u of x, which is the Robin harmonic measure of a set E, where E is a fixed Borel subset of the boundary, then this U solves the Robin problem with the f, which is the indicator function of U. Okay. Now a question. Do we have a probabilistic interpretation? Right, in the Dirichlet setting is still on the blackboard. We have this sort of nice interpretation in terms of Brownian motion. Okay, so here so far everything I said is essentially very equivalent to the Dirichlet setting. Probabilistic interpretation is complicated. So intuitively, there's a thing that happens. So you get the domain, you get Brownian traveler started at the point X. When at first you get to the boundary, you flip a coin, an unfair coin, and with probability P, you get absorbed. And with probability 1 minus P, you get reflected back.
I guess that here the matrix A is meant to be the identity, right?
Hmm?
Like for this part of
Yeah, you can think of it as identity. Otherwise, you have some some things in the interior, but it's yeah. Okay. So once you get that first point to the boundary, you either get killed there or you bounce back and then you restart. Okay. Then sort of the parameter A in our problem is the ratio of these two probabilities. This is not rigorous. Okay, I'm just saying heuristically this is true. Just a sanity check. If you're absorbed with probability 1, then you are in the Dirichlet setting, right? Which makes sense because then this A is infinity, which is consistent with what I said. And if you're reflected all the time, if you're never absorbed, this is the totally reflecting Brownian motion, which corresponds to the Neumann problem. Okay, there's no transfer across the boundary. The normal derivative is 0, so there's no flux across the boundary. Okay, so this makes sense intuitively. It's not a theorem. Okay. Partially reflecting Brownian motion, it's kind of complicated to construct from a point of view of probability, especially in these rough domains, and I'm not aware of anyone that does it, really, in the level of generality we want. it's something I'm interested about, and if somebody knows more probability than I do wants to talk about it, I'm very happy to. But so what I would like is actually a Kakutani theorem. So something that tells me this is actually, you take partially construct partially reflected Brownian motion, and then this Robin harmonic measure is really the hitting measure of partially reflected Brownian motion.
So when you're saying there's not that theorem, is it? I mean, is the problem in the regularity of the boundary? I mean, would you have that theorem if you're like on smooth, or there's a problem even there?
This is a good. So it's not. I think yes, but I don't think even there it's written down even for smooth. But at least like if the domain is smooth enough, like Lipschitz is enough, at least you can construct a partially reflected Brownian motion.
Okay.
And then it's okay.
So morally, it's the regularity.
Yes. Yes. Okay. There is a paper, sort of joining toward this. There is a paper that constructs a partially reflected Brownian motion. It's by Bass. So these are probabilists, Birdsey and Chen. 2008, where they construct this partially reflected Brownian motion in a class of domains. And they also, in that paper, they ask this question, which is very related to what we do. So you have your domain omega. Say you have a little ball B inside the domain omega, and you consider this problem. So harmonic function in omega, which is sort of 1 on the source B with homogeneous Robin data at the boundary of omega. So in this paper, where they construct this partially reflected Brownian motion, is to address this question for which domains is the infimum over the boundary of U strictly positive. Okay, note that this is equivalent, since it's a Robin problem, to the infimum, let's say, probably. Let's say, that's the supremum, maybe. Or okay, let's say. Oh, the normal derivative of U being nowhere 0. Okay. So in the sort of in a physical interpretation, this is what you want, because if you points where the normal derivative is 0 is where you have no flux through the boundary, so it's kind of an inefficient use of material, if you will. Okay, and they sort of answer these questions. They construct some class of domains which are well approximated by Lipschitz domains in a sort of very ad hoc sense, I think, that I haven't seen in other papers. And it's also interestingly, they constructed samples of cusps for which you do not have this property. Okay, so my assumptions here, you need some of it. There are some cusps in which, for instance, which are bad for this problem, which is not our problem of harmonic measure, but it's very close to it. You can think of it as this is kind of like the Green's function, kind of. Okay, so our second theorem that I want to tell you about is probably you can already guess what it is that if we take AR D minus 1 AR plus interior postgres plus Harmonic chains domains satisfy this property. So this property is called being active. So we can say that our domains, the ones in which we set the problem, are active. Okay, experts will probably recognize that this is nothing more than a Harmonic inequality up to the boundary. Okay. Saying that the infimum of U is strictly positive at the boundary is really a Harmonic inequality. And so this is what we do. Sort of a little bit, this Harmonic inequality up to the boundary can only be true at small scales. If you think intuitively, at large scales, this behave more like the Dirichlet problem, and then the Harmonic inequality up to the boundary is clearly not true for the Dirichlet problem. I mean, it's through a comparison principle, but this is let's see, how am I doing on time? I got like 10 minutes maybe. Okay, this was this thing of buzzwords in Chinese question was not our main objective, but it's sort of something we stumbled upon. And I mean, we needed this Harmonic inequality anyway, so we thought it was kind of nice. But yeah, especially I think this paper is especially interesting for the examples of the cusps, in which this thing does not happen. Okay, let's see. Now I actually. Most of the results I told you about so far have been maybe kind of expected. Now I'll give you something unexpected. Here. This is maybe our main result. That tells you, so let's say omega, I'm gonna say as above. It's not above, but it's to the left, but it's the conditions that are still on that blackboard. And again, I remind you that the Robin parameter here is strictly between 0 and infinity. Then we have that the Robin harmonic measure is mutually absolutely continuous with respect to surface measure, with no rectifiability assumptions. Okay, if you're used to the Dirichlet harmonic measure, and I tried to give you a primer on that, this is very surprising because of the results that I mentioned before. It essentially tells you that this thing is true provided you have rectifiability of the boundary in some sense. Okay, here we're saying that this is once you have like that little bit of topology and regularity of the boundary, then you have mutual absolute continuity of the surface measure with respect to harmonic measure, harmonic measure. Okay. In particular, let me give you an example of something that satisfies these assumptions that is certainly not rectifiable. Something called the four-corner counter set. So this is here. Take these four corners, then iterate this construction. Okay, you go on. So you take the complement of the things you take away. This is called the four-corner counter set. Well, then this thing satisfies our geometric assumptions, our topological assumptions. But it's what is called purely unrectifiable. Okay, so it's very, very far from being rectifiable. So the theorem that's above, this theorem here works for the four-corner counter set, for the complement of the four-corner counter set. Okay, so the Robin harmonic measure will be mutually absolutely continuous with respect to surface measure.
Is it special to this particular construction or not?
The four-corner counter set? No. This is as any domain omega that satisfies those conditions will have this.
Can you just give us an example?
Yeah, this is just an example of something that this is certainly not true for the Dirichlet harmonic measure.
But could it lie on your definition of boundary condition?
Yes,
Because you're forcing me to actually integrate also on those sets, right? In your definition of Robin boundary
Yes.
condition. Whereas in the Dirichlet boundary condition, I'm not sure the way you understand the boundary condition, actually, you would even see that set,
right.
You really wouldn't see it.
Right. So another way I think about it which is like more informal sort of, but in this sort of probabilistic idea that is not rigorous is something like, okay, there are parts here that are sort of shielded for the harmonic measure, but if you're allowed to keep on bouncing with positive probability, then eventually you reach everywhere. Might take you like a lot of time to get there, which is something that I think actually could have an interesting mathematical meaning for like It's like studying sort of the local time at the boundary and this kind of things. We haven't done that.
Could you explain that a little better?
Sure.
I think, I just can't quite grasp what the iteration scheme is.
Oh, yeah. All right. So I guess you take the square, you divide it in 9 smaller squares. You take the 4 corners,
Yeah,
and then you iterate again, right?
but
You remove the cross.
you remove,
Yeah.
you remove the cross, but that leaves one, that's right, you remove the cross, but
Yes.
that leaves up the thing on the corner hanging not unconnected. That's what I wondered.
Yeah.
Yeah. So what yeah.
Oh, it's not, oh.
So the domain we consider is the complement of that thing. So it's like, it's all the crosses instead.
Oh, really?
Right, yes. And the boundary of the domain is this, these 4 corner counterside, yes.
I see
Yes.
what I'm doing. Okay.
Thanks for the question. Okay, let's see, I'm essentially done. Let me mention. We have also a quantitative version of this. Again, sort of the same geometric setting as all the. Let's see, I'm just gonna be. What do I wanna do? I'll try to be informal. So I take a point x naught on the boundary, I take a Borel set contained in the ball of radius x naught, Borel center x naught, radius r. Take points x. Set the larger ball, and I'm gonna give you something that look like A infinity conditions. They're not A infinity conditions because they're not scale invariant. I'm gonna comment on a second. Let's see. If the ratios of the observed measure of the set E and that of the ball of radius r are less than a constant that depend on the product of the parameter A with the scale r, then we have smallness of the ratios of the harmonic measures. And there's also sort of vice versa, if the ratios of the harmonic measures are small, again with the constant that depends on the product of the parameter A and the scale, then are small.
You need to intersect HD minus 1 of the ball with something.
Oh, yes, with the boundary.
With the boundary,
Sorry,
okay.
yeah, with the, right. Okay, so if we didn't have this, if the constant did not depend on the scale, this would be something like an A infinity condition. The problem is that this Robin harmonic measure is not scale invariant. Okay, if you take, what do I want to say? Right, so you have, in general, if you take the Dirichlet problem or the Neumann problem, there are scalings that leave the problem invariant, right? In the Dirichlet case, if you take, you have Rx, which is U of Rx, this leaves the Dirichlet problem invariant. In the Neumann problem, you take, I don't know, U tilde R of X, which is Q Rx over R. This leaves the Neumann problem invariant. Whichever one you take in the Robin problem, will give you something. So if you take the rescaling, we give something with Robin parameter AR. Well, let's say UR. Right. So if you try to rescale the Robin problem, you get a Robin problem with a different parameter in which the scale comes into the parameter. Right. And this is sort of has to be necessary because the scalings, the invariant scalings of the Neumann and the Dirichlet problem are different. The Robin problem has to interpolate between the two. Of course, you have to, you have to have something. Okay. So
your beta is a function which is not depending on A. That's what you're saying.
It's depending on AR, on the product of AR. It's actually precise. We have it's not just yeah.
But it's just a function. So if A is equal 1/2 or A is equal 1/4, it's the same function.
So I can actually tell you. So this, for instance, let's say if AR is less than 1, this is really delta times AR.
Okay. Yeah.
Yes.
So it's okay.
Okay. Yeah. If AR is greater than 1, this is delta over AR.
Okay. Yeah. So it's a function of AR.
Yes. Okay. Sort of both these two results are surprising. Both, as I said, because of the rectifiability that is not here. But also, if you think about it, everything I said works for the case of like uniformly elliptic bounded symmetric matrices, which also for the Dirichlet problem, things go massively wrong there. So there I wrote the Dirichlet problem just with the Laplacian, but you can do it with dv grad u. And then there are examples of like Modica, Mortola, Caffarelli, Babes, Salsa maybe. That tell you that if you have a continuous matrix, then you might have the Dirichlet harmonic measure with respect to that matrix and the surface measure to be, even in the ball, to be not mutually absolutely continuous. Okay, so there's this result is surprising somehow, both from the missing geometry in that we don't need any rectifiability, but also there are no conditions on the matrix A. In the Dirichlet case, you need pretty strong conditions on the matrix A to make sure that the things that are true for the Laplacian go through, like Carlson perturbations of the identity, essentially. Okay. In our setting, we just need the. Okay, I'm done. Let me just mention sort of what is not the proofs, because there's certainly no time for that, but sort of the mechanism behind the proofs, which I think is kind of interesting, is that if you take the function u, which is Robin harmonic measure of E, is the unique minimizer of a function. And the functional is this, call it J E of U, which is 1 over A u minus 2 integral over A of U plus integral over the boundary of U squared. So you construct this harmonic measure as we did before in the theorem, and then we find out that it's a unique minimizer of this functional. It's a free functional. Okay. And this is sort of the key to the proof of these two theorems of mutual absolute continuity. In one case, you can see it pretty easily, I guess. In the qualitative case, for instance, imagine that the Hausdorff measure of E is 0, right? Then this term goes away, then tells you that omega r x of E is also 0. Right? So it's sort of, and then also, the quantitative statements are also gotten out of here, but playing with test functions in this functional in a little bit more.
That's kind of better than 0. So I mean, if you don't have the integral over E, then you don't see it.
Yeah. Mm-hmm. Yeah. So that's all I want to say. I'm happy to take questions should there be any. Thank you.
in harmonic vectors,
Sorry,
continuity of the coefficients is not enough. 100 would be enough
for what, sorry?
for the, for changing to the Laplacian to something else.
You mean in the Dirichlet setting?
Yeah, the Dirichlet setting. Saying there are counter examples with continuous coefficients. Is it
Yes.
really,
Good question. I don't know if there are counter examples, but I expect it. Maybe, do you know, Amanda? Maybe it.
This DKP condition.
Yeah, exactly, which is like, so it's essentially in Carlson, like, I mean. Yeah. I don't know if like somebody has explicitly written down the counter examples for older, but. Yeah, I don't think it's true. I don't think there are.
I saw somebody raising their hand.
Yes.
Yeah.
So it was, I was curious about what you had in mind about this reflected Brownian motion. For example, dimension 1, is it clear what this is?
So in dimension 1, you mean the domain is dimension 2 and the boundary is dimension 1, or you mean the domain is dimension 1?
Yes. This should be the baby case.
Yeah, you're right.
That's just what you had in mind.
You're right. It's a good question. I don't know what it looks like. Yeah, maybe it's word. I don't know if you can get something out of it for the. Yeah.
You get just by reflection, right?
Reflection of time, right?
Yeah.
Yeah. But I don't know if it tells you anything about.
Markovian at least?
But the problem is like, aren't harmonic functions trivial in dimension? I mean.
I'm not
Yeah,
saying
in dimension 1 harmonic functions
Yeah.
are linear, yes.
But
I mean, that.
I mean, okay, it doesn't have to be straight, but
Right, but I guess the Brownian motion still
yeah.
is like.